Good morning to all. So, in today's lecture, we are going to study state space technologies or techniques in the regulatory design. So, we know that the alternative to the transfer function approach to a control system design is the state space approach. The transfer function approach depends upon polynomial algorithms which are slow to emerge, and in contrast, the linear algebraic tools that are required by the state space techniques are a lot more advanced. So as a result, many more control design techniques are available in the state space approach. So at the current state of development, the state space techniques are preferred over the transfer function approach, especially for multivariable systems. Now here in this topic, we briefly summarize the state space approach to the regulator design. Okay. So now, in case of regulator design, by using state space approach, here we are going to use the combined control law and estimator. Okay, I'll explain what it is. So we will combine the state feedback controller and the state estimator, okay, to arrive at the overall controller design. So for that we will use the separation principle. Okay, using this separation principle, we design the controller and the estimator separately. Then we combine them and produce the overall controller, which will be referred to as a compensator. Okay, and lastly, we are going to have a look on example, okay, of a controller, design of a controller or compensator. So now we state the important result known as the separation principle. Okay, so in this case, the state feedback controller can work only if all the states are available. Okay, so while designing the controller, we assume that the states are estimated by an estimator. Okay, and next we look at the assumptions involved in the use of the estimator. So it is possible to estimate the states only if the states are bounded. Otherwise, if the states are unbounded, it is not possible to estimate the states. Okay. So now in this case, we will assume the stabilizing influence of the controller to keep the states in the bounded condition. Okay. Now our controller assumes the existence of the estimator, and estimator will assume the existence of the controller. Now this separation principle which we are going to use here, it allows us to design the controller and the estimator separately. Okay, obviating the need to design both of them simultaneously. So without this result of separation principle, the state feedback controllers would have become a lot more difficult method to design. So you can see here this figure, I'll zoom it. So this is the block diagram of the state feedback controller and the estimator combination. Okay, so this is the state feedback controller, this is the estimator, and this block, okay, within the dash line, okay, this red dot dash line, the two blocks constitute, or it indicates the compensator, okay, which is very similar to the conventional output feedback controller. So the plant is described by A and B. Okay, here A and B, you can see A and B. Next, okay, so all the states are not measured over here, only the output Y is available. Okay, so we assume that a prediction estimator is used to estimate the X, okay, X value. So we are going to use a prediction estimator, current estimator, okay, to find the value or to estimate the X. The input U, you can see here the input, plant input U of K or U, that goes into the plant is also sent to the estimator. Okay, so this is having two ways. Okay, first one, it goes to the plant and it is also sent to the estimator. So the plant output becomes another input to the estimator. So this plant output y of k is another input to the estimator. So using this, the prediction estimator gives an estimate of the state vector, okay, which is denoted by x bar. X bar is a state vector, and the control law works on the basis of x bar and produces the control effort u. Okay. So in this figure of the block diagram, okay, we can see the blocks that implement the controller and the estimator are inside the dash line, okay, as I already said. So we will refer to this combined block as a compensator. The plant output y is an input to the control effort u, okay. Plant output y is the input to the control effort u, and this u is the output from the compensator, okay. Output from the compensator is u to the plant, from the input output viewpoint, okay, is similar to the traditional feedback controller. So now we are going to derive the transfer function of the compensator, okay. Because we are using state space approach to the regulator design, we are going to have a look on the derivation or designing of transfer function of the compensator. Okay, this is the theory here. If you want, you can have a look on it. Now a general control law is defined by using u, okay. U equals to minus kx plus v, okay. It is a general control law in a general form. So now if we take as this v equals to 0 and we use x bar in case of this x, we will get this equation number 1, okay. You can see here u becomes minus k x bar of k, okay. So v is 0 and x is replaced by x bar. So as I told earlier, there is a feedback loop. So now it is okay to substitute for u, okay, in the state space equation as. So now we will substitute the value of u in a state space equation, okay. So state space equation is given as x of k plus 1 equals to ax of k plus bu of k. This is a simple state space equation, okay, and we are going to put the value of u, okay, here. So now put u equals to minus kx bar, we will get the equation, okay, x of k plus 1 equals to a x of k minus b k into x bar of k, which is the value of u. This is the equation number 3. So now for the design purpose, we require the difference between the estimated state and the normal state, okay, which is the error x cap, okay, this x bar. This is the error which is the difference between the estimated state, okay. This is the estimated state, this is the normal state, okay. So x bar can also be written as this error minus this error plus the estimated state or the normal state, okay. So now after putting x bar value, this value in equation number 3, we get, so just put it, x of k plus 1 equals to a x of k minus b k, okay. Just put this value here, it will become b k in bracket x of k plus, okay, error, which is equation number 5. Now we know that the prediction estimate, okay, the prediction estimator make the use of measurements, okay, taken up to the sampling instant k minus 1 to estimate the value of x of k. So therefore x of k plus 1 equals to ax of k plus bu of k, and y of k equals to cx of k. Okay, state space equation in a sampling. Okay, so here y of k is a scalar. Okay, also the obvious choice for the estimator is to explore whether the plant model can be used for the estimation itself. Okay, so to explore whether the following model can be used, this model can be used as an estimator of the states. Okay, just give it x bar. Okay, x bar of k plus 1 equals to a into x bar of k plus b into u of k, then y bar of k equals to c into x bar of k, where a and b are, and also u of k are known. Okay, so here one thing we have to note that the initial states, okay, that is x of 0 and x bar of 0 are the same. Okay, so then x bar of k will be the same as that of x of k. Okay, x bar of k will be same that of the x of k, because initial states are the same. So by using the combination of this equation plus this error equation, okay, from the above model we get that x cap, if this is error of k plus 1 equals to a minus LPC x bar of k. Okay, x cap of k. This is equation number 6. So this equation has been founded by the use of this model and this error equation. Okay, so if x, okay, by x, this error is equals to 0, system is asymptotically stable. Now we are going to stack equation number 5, okay, this one with the error, and equation number 6, this equation. Okay, we are going to stack them like in a matrix format. So left hand side x bar of k plus 1, okay, for this, and x of k plus 1 for this equation. Okay, left hand side equals to the coefficients, so a minus LPC, then 0, then bk minus bk, and then again a minus bk, and the output. Okay, and then the coefficients x cap of k, okay, this one, and x of k over here. So put this as equation number 7. So we can see here the system dynamics are represented by 2n difference equation. Okay, where n is the dimension of the state vector, and if we measure all the states, however, we need to use only n difference. Okay, n difference equations to describe the dynamics. So now there is a trade-off in and so there is a trade-off in not measuring the states of the system. Okay, so that we have to deal with the larger dimensional systems. So in the next step we will verify that the poles of this augmented system, okay, this system, are indeed at the locations we want them to be. So the characteristic equation of 7 means, okay, this characteristic equation of 7 is, so Zi is been multiplied into this box. So Zi minus a plus LPC 0 bk, okay, and Zi minus a plus bk. Okay, so minus Zi has been multiplied into the box. This is, okay, now it is equal to 0. We can write this equation as, okay, just the two of the terms, okay, this one and this one, because of the 0 matrix in the upper right. Okay, this equation can be written as separately Zi minus a plus LPC, okay, and Zi minus a plus bk equals to 0, equation number 8. So now we have to look on the estimator characteristic polynomial that are AC of z and AE of z. So both are same, okay, and both are 0. So this is equation number 9. Now we proceed to find out the transfer function of the compensator. One thing I would like to tell you that this, okay, this indicates equation number 9. This shows that the poles of the second, 2n dimensional dynamic equation, okay, which will describe the feedback system, are precisely the locations where we have to place our state feedback controller and estimator poles. So now after this indication and this equation number 9, we proceed to find out the transfer function of the compensator, okay, which is given inside the dash lines, okay, as I told earlier, dash line, which consists of control law and estimator. So the states of the estimator are described by x bar of k plus 1 equals to a into x bar of k plus b into u of k plus, okay, this constant LP in bracket y of k minus c x bar of k. Now we can replace this u of k equals to minus k x bar of k, okay, in the next line, again the remaining equation as it is. So after simplifying this equation, we obtain the state equation for the controller. So it will be, okay, just take the like terms, like for example take the common terms. So coefficients for x bar and this x bar are a minus bk, and then this is x bar, okay, so LPC is a common. So x bar of k coefficients and y of k coefficients, only LP is there for y of k, which is a constant. So equation number 10, after simplifying this equation, we can find out. So the input to this compensator, okay, this compensator is y, and the output from this compensator is the control effort u, okay, which is represented in the block diagram. So the output equation, this u of k equals to minus k bar of x, already we have seen this. So the transfer function of the compensator is given by, okay, GC of z is the transfer function of the compensator, okay, which is output upon input, okay, in terms of z. So equals to minus k zi minus a plus bk plus LPC inverse LP, okay. So this equation number 11 is nothing but the combination of equation number 8, okay. They have taken all the terms, okay, just, okay. So now this equation number 11 is the transfer function of the compensator. This is what we require, okay. It is equals, we can equate this equals to 0 also, no problem. So by looking at this equation, okay, we can recall that we have designed the state feedback controller such that the roots of this 2 are at the required locations, but now we have a different characteristic polynomial, okay, which is this one, okay, zi minus a plus bk plus LPC, okay. This is the characteristic polynomial which is different. So where will its roots lie, okay, where are the roots of this are lying? So the answer is that there is no guarantee that these will lie inside the unit circle, okay. So in other words, the compensator by itself would be unstable. This is another price we pay for not measuring all the states, okay. So state measuring is very important term or very important phenomena. So now we should have a note that the original state feedback controller is of constant gain of k, which is stable, okay. This k is stable, and it should be emphasized that although the compensator by itself could be unstable, the closed loop system is stable. Okay, which is indicated by its characteristic polynomial, okay, which is this in this equation. Okay, so it ensures that the closed loop system is stable. So now there is a question that arises that where we should choose the poles of the regulator and the estimator. So when measurement is noise or so when measurement noise is not an issue, it is convenient to pick the control roots to satisfy the performance specifications, okay, and also actuator limitations, and then to pick up the estimator route somewhat faster by factor of 2 or 4, okay, which indicated by the rise time, so that the total response is dominated by the response due to the slower control poles. Okay, so now we are going to have a look on the example. So now we have to determine the compensator of the system. We have this equation, okay, and we have the different polynomials, okay, or the states. So A is given, B is given, C, K and LP is given. Now we have to determine the compensator of the system. So we know that already compensator of system is GC of Z equals to this equation number 11. So just write it down as it is, then put the values. Okay, so firstly find out this, okay, subtraction. So A minus BK minus LPC, so just put the values, okay, and we get the value of A minus BK minus LPC, this value. Next we have to find out this whole, okay, without minus K. Okay, so here you can use this. So after finding out, just we have to multiply Zi. Okay, so I is a, as we know, polynomial, okay, unity matrix. Just put the values, okay, we will get this 4, okay, as a this 2 by 2 matrix, and inverse of this matrix if we take, okay, just cross multiply this one. So 1 upon this equation becomes this quadratic equation, then the remaining as it is. Okay, so this is the inverse, and after, okay, multiplying this to each other, we will get this as an answer. This is the controller. Okay, so here minus K is not taken, so we can also ignore this LP and minus K because it is already in the, okay, we can only take this much inverse characteristic equation, okay, polynomial, to find out this compensator. Okay, so this is regarding the concept of state space approach for the regulator design. So if you have any doubt, you can ask, and do watch this video and try to solve this problem, and you can also try to derive it, okay, derive these equations for your convenience. This is very important as per the examination is concerned. Okay, so till then, take care and goodbye.